In this class we will take microscope, and we all are aware of this instrument. You might have used in class 10 this. And even a single glass, magnifying glass, which is a convex lens, that can also be called a microscope. This is called simple microscope. The function of microscope is to see very small objects. Even magnifying glass, you might have used it many times. We use this to see very small objects. Whenever the object is kept very close to this lens, between focus and optical center, we get a magnified image. So even a single convex lens can be called a microscope. Otherwise, if we want to magnify the objects further, and we need more, very high magnifying power, then a single convex lens will not be sufficient. Then we use combination of lenses. We use more than one lens. That will be called compound microscope. So first let me take simple microscope. Simple microscope means a single convex lens. That's it. This is the optical center, and let this be the focus of objective. Just one lens is there. We will call it objective lens. Okay. If the object is placed here, we will get a magnified image. We get a magnified image even when the object is kept at focus. In all these instruments, microscope as well as telescope, I will take two positions for the final image. One, when the image is formed at infinity, and one, when the final image is formed at least distance of distinct vision. When the final image is formed at infinity, we call it normal adjustments. So for microscope as well as for telescope, we will take two cases for final image formed at infinity and one final image formed at least distance of distinct vision. So let it be the case when final image is at, when the final image is at D. D means least distance of distinct vision. Okay. Parallel line will pass through focus and a light ray passing through the optical center. This is the parallel ray to the principal axis, which will pass through the focus of the convex lens, and a light ray passing through optical center will go straight. From this side, they are diverging. If I extend them for wherever, don't force them. So this is the final image. A, B is object, and A dash, B dash is the final image. Okay. And we are saying the final distance is formed at least distance of distinct vision. Okay, now we have to find out the magnifying power of this instrument. How we define magnifying power? It is the ratio of, we did it in last class, ratio of the angle subtended by the final image at I and the angle subtended by the object at unaided eye when the object is at least distance of distinct vision. Why? This is the angle subtended by final image at eye to the angle subtended by the object at unaided eye. Unaided eye means when we are not using the lens. When the object is at D. The purpose of writing this part when the object is at D, because we have to see what is the maximum size of the image without using the instrument and then using the instrument. That will give us the magnification power. So first of all, keep the object at distance D. To find out this angle, let me call it, and for small angles, these will be taken as tangent theta. Small angle and tangent will be same. This is the final image. This is, I will be very close to this lens, so let this be theta. Image, angle subtended at this lens, so tan beta. And for alpha, let us keep, I am drawing the diagram separately. You can draw it here too. Keep the object at distance D and then measure the angle. This is tan alpha, which is AB by D. But keep in mind, when the final image is formed at least distance of distinct vision, then at that moment the object is not at a distance of D. Object is at some other distance. You have to first keep the object at distance D without using this. At 25 centimeters, see what is the visual angle and then use the lens. Now adjust the distance till the final image is at D and now measure the angle. The ratio of these two angles will be the magnifying power. Tan alpha is this, tan beta is, let us use this diagram now. Tan beta will be A dash B dash upon D. So magnifying power will be tan beta by tan alpha. So A dash B dash upon D, AB by D, so it is A dash B dash upon AB. No new result actually. A dash B dash is the height of the image, AB is the height of the object. This is the magnifying power that we have done even in case of lenses. And what this ratio is A dash B dash upon AB. We can use the property of the similar triangles. This by this. Actually it is V by U. V is this distance and U is this distance. Okay. We don't know this, but this is known to us. So use expression one upon U is 1 upon V minus 1 upon F. So we shall be using it here. V and 1 by U is 1 by V minus 1 by F, and it becomes 1 minus V by F. Now substitute the values. 1 minus, with sign convention, what is the value of V? It is minus D by F. So M is 1 plus D by F. So this is the magnifying power of simple microscope when the final image is formed at infinity. Now what if the final image is formed at, it is when the final image is formed at least distance of distinct vision. Draw the second diagram when the final image is at infinity. Case 2, final image is at infinity. This is the case when the final image is formed at infinity. The object needs to be at focus. So now this time this is beta. So what is the value of tan beta? AB upon F, and tan alpha, again using the same this is the diagram that I used. So tan alpha is AB by B, and M is tan beta by tan alpha. So it is AB by F, and this is AB by D. So it is D by F. We are using single lens, so 1 plus D by F when the final image is at least distance of distinct vision, and M is equal to D by F when it is at infinity. Now if we need higher magnifying power, then single lens may not be enough, and we need two lenses now. We call it compound microscope. We have two lenses, and again case 1, final image at least distance of final image at least distance of distinct vision. Two lenses, one is called objective, another is eyepiece. The lens which is kept towards the object is objective, and keep in mind we are using microscope to see very small objects, so objective needs to be very small and also of less focal length. We have two lenses now. So focal length of objective is less than the focal length of eyepiece, and even the size. So aperture also, objective is small aperture and eyepiece will be of large aperture. Okay, now see what will happen. Object is placed beyond focus. Parallel light ray will pass through focus, and a light ray passing through the optical center goes straight. This is the image formed. If this is AB, let me call it A dash, B dash. And now make another lens here. And it should be kept in such a way that this image formed by the first lens, objective, lies between the focus and the optical center of the second lens. So it means this lens is simply acting as a magnifying glass. For this, the object is this one. So for this lens, the object is kept between the focus and the optical center. Whatever we did when we studied simple microscope. Okay, now these rays, don't leave them in between. Where will the final image be formed? Parallel ray, if any, I can take one ray like this. parallel one will pass through FE and one will pass through this, and wherever they meet, wherever they may meet here or here, A dash B dash, this is A double dash and B double dash. And I can complete even these rays and so on. Even this ray can be completed. Okay, now to find out magnifying power again here. This is the final image. So this is beta. Angle subtended by the final image. I will be very close to this lens. This is called eyepiece lens. Okay. And for alpha, we will again take the same approach, keep the object at least distance of distinct vision, D, and tan alpha is AB upon D. Find out the magnifying power now. Tan beta is, now see from here, tan beta. We have taken that the final image is formed at least distance of distinct vision. A dash, A double dash, B double dash divided by D. Tan beta. This is perpendicular, this is base. I am taking this triangle. O2, O1, B dash, B double dash. Okay, and tan alpha, we have AB by D. So M is this divided by this. We got, this can be written as A double dash B double dash upon A dash B dash into A dash B dash upon AB. I have multiplied and divided by A dash B dash. What difference does it make? What is A double dash B double dash upon A dash B dash? This by this. This is actually the magnifying power of eyepiece. And A dash B dash upon AB, this is the magnifying power of objective. So it means when we use two lenses, the magnifying power of the microscope is the product of the two. So if one has magnification 3 and another one has 4, so combined will have 12 times magnifying power. It is the product of the two. And now no need to derive any further thing because we have already done it. Magnifying power of a single lens, ME, when the final image is formed at D, the object is placed between focus and this. We did it for simple microscope. What is it? 1 plus D by F. E I will write now. And MO, this is the magnifying power. This I can write it VO upon UO. If I am writing with sign convention, U is minus, V is plus. So one minus sign will come here because of this. This will be negative. So magnifying power of microscope when the final image is formed at least distance of distinct vision is this. VO by UO 1 plus D by FB. Second case, when the final image is formed at infinity. Now we have to adjust the distances in such a way whenever you are drawing these diagrams, please use scales and pencil. The distances should be accurate, otherwise you will not get the proper ray diagram. Okay. Now this is image formed by the first lens, which is A dash B dash. This is at the focus of this lens. So what happens whenever the object is at focus? The image is formed at infinity. This is how the image will be formed. All these rays will be parallel, and this angle will be beta. So what is tan beta now? It is A dash B dash upon FE, because this distance is FE. And tan alpha, same, AB by D. So M is tan beta by tan alpha. A dash B dash by FE, and this is AB by D. So VO by UO D by FE. This is the magnifying power of microscope when the final image is formed at infinity. Sometimes this expression is written in terms of tube length. Tube length means the distance between the two lenses. If I use a letter L, tube length, then see, for maximum magnification, we always try to keep AB very close to F. And also this image is very close to this, so that we have maximum magnification. So actually VO, this distance is almost L, equal to this, and UO is also almost equal to F. This is kept very close. So M can be written as minus LD upon FO FE. LD upon FO FE. So see here, the magnification is inversely proportional to the focal lengths of both the lenses, FO as well as FE. So both the lenses in microscope have smaller focal lengths. Okay, it's all about the compound microscope. We have done the simple microscope, then compound microscope, two cases in each. In simple microscope, the magnifying power is D upon Fe and 1 plus D by Fe, depending on whether the final image is at infinity or at least distance of distinct vision. And same way here, it is VO by UO 1 plus D by Fe or VO by UO D by Fe. Next we shall take telescope.